Okay. Adjacency matrix of complete graph KL is the matrix of ones minus the identity matrix. That is where the diagonal is 0, since it's a simple graph, and every vertex of the complete graph is adjacent to every other vertex. Therefore, you have ones everywhere except the diagonal. Now, the result is stated to be that the nth power of j minus I is j times the following constant plus minus 1 power times I. This is the result. Now we will prove this result. Since the nth power of the adjacency matrix contains every element of the nth power of the adjacency matrix is the number of walks let me write that down. The ijth entry of adjacency matrix power n is number of walks from I to j in n moves. Of n length. A walk of n length, number of walks of length n is the nth power of the adjacency matrix. The ijth entry of a power n. We will prove this result. Now, let's find the eigenvalues of j minus I. We have to find this will give you the characteristic polynomial of the matrix J minus I. Okay, now we have to find out when this determinant is 0. Okay, when x is minus 1, we have a determinant of all the matrices of 1. When x is minus 1, all the elements, all the rows and columns are 1. In such a case, the determinant is 0, since all the rows are repeating. Since every row, since L minus 1 rows are repeating a repetition of the first row, we can say the rank of this matrix is 1, and the nullity is L minus 1. So therefore, multiplicity of the root x equal to minus 1 is L minus 1, the algebraic multiplicity. So you can say that x plus 1 power L minus 1 is a factor of this matrix. Yes, so x plus 1 power L minus 1 is a factor of the characteristic polynomial of the matrix J minus I. Now case 2, when x is equal to L minus 1. In such a case, you have 1 minus L as the diagonals, and you have all the ones here. Now, let us conduct the row sum operation. R1 goes to R1 plus R2 plus R3 till RL, where the first row is equal to the sum of all the following rows. Then what do you get? 1 minus L plus summation I goes from 1 to L minus 1, 1. Plus, okay, so this, then this is your first row, first column entry. Then next is 1 plus one minus L, and so on. So this is 0, this is also 0. So you get the following: where the determinant is the same as 0, 0, 0, 0, 1, L minus 1, L minus 1 as your matrix. So therefore the determinant is 0, since this row has all the zeros. So therefore x equal to L minus 1 is an eigenvalue of the matrix with multiplicity 1. Therefore you can write the characteristic polynomial. Therefore the characteristic polynomial will be a multiple of x plus 1 power L minus 1 times x minus L minus 1. So the characteristic polynomial is divisible by this polynomial, and since the multiplicity is L minus 1 and 1 here, the power is 1, the sum total is L, and we have L roots. Since the matrix is L cross L, we have L roots. Therefore the eigenvalues are minus 1 and L minus 1. Since the eigenvalues are minus 1 and L minus 1, every entry of j minus I is a linear combination of the nth power of j minus I is a linear combination of the nth powers of the eigenvalues. Every ijth entry of j minus I power n is nothing but alpha times L minus 1 power n plus beta times beta times minus 1 power n. Now, since j minus I power n, the diagonals of j minus I power n is the number of closed walks, and we know that all the closed walks in KL, all closed walks in KL, whether it's 1 to 1, 2 to 2, 3 to 3, and so on, have the same number of walks. Let me show you an example. In K4, this is K4, a complete graph of 4 vertices, whether it's a closed walk from 1 to 1, or a closed walk from 2 to 2, or closed walk from 3 to 3, or closed walk from 4 to 4. It will have the same number of walks. Therefore, you can say that all the diagonals of j minus I power n will be the same. Similarly, number of walks from 1 to 2 will be the same as number of walks from 1 to 3 and number of walks from 1 to 4 in n moves of n length. Therefore, all elements that are non-diagonal will also be the same. Since one can take the automorphisms of kn and it will not change. Every permutation of kn, every permutation of the complete graph kn is an automorphism of the complete graph. Therefore, every non-diagonal element of j minus I power n will be equal Now let's assume f open of n and f closed of n. Where let f open of n be the number of open walks of n moves of the KL graph, and let f closed be the number of closed walks, so f open of j, so j minus I power n will simply be f closed of n in the diagonal and f open of n in the non-diagonal. Now f open of 0 is obviously 0, because you cannot move to a different vertex in 0 moves, whereas f open of 1 is 1 and f closed of 0 is 1, whereas f closed 1 is 0, because it takes 2 moves to move to a different vertex and come back to the original vertex. So alpha 1 L minus 1 power 0 plus beta 1 minus 1 power 0 is 0, which implies alpha 1 equal to minus beta 1. Alpha 1 power times L minus 1 plus beta 1 times minus 1 is 1. We get the following: alpha 1 times L minus 1 plus alpha 1 equal to 1. That means alpha 1 times L is 1, alpha 1 is 1 by L, and beta 1 is minus 1 by L. So you have f open of n as 1 by L times L minus 1 power n minus minus 1 power n. And for f closed, well, you have alpha 2 L minus 1 power 0 plus beta 2 times minus 1 power 0 is 1. That means alpha 2 plus beta 2 is 1, and alpha 2 times L minus 1 plus beta 2 minus 1 is 0. Minus beta is nothing but alpha 2 minus 1. So alpha 2 L minus 1 plus alpha 2 minus 1 equals 0. Alpha 2 L is equal to 1. That means alpha 2 is 1 by L. Beta 2 is 1 minus 1 by L, which is L minus 1 by L. So you have f closed of n as 1 by L times L minus 1 power n plus L minus 1 times minus 1 power n. So therefore j minus I power n is nothing but one can write this as 1 by L times L minus 1 power n. Well, 1 second. Okay, F closed one can again rearrange and write 1 by L minus 1 power. If I take L times minus 1 power n outside, you simply get F open of n plus minus 1 power n. So one can write j minus I power n is nothing but since F closed is F open plus minus 1 power n, we can write j minus I, since j minus I power n is nothing but F closed. In the diagonal, we can write this as F open plus minus 1 power n and F open of n. In the diagonal, we have F open plus minus 1 power n, and in the non-diagonals we have F open, and in the diagonals we have F open plus minus 1 power n, which is nothing but F open times j plus minus 1 power n I, since minus 1 power n is added only in the diagonals. Now this is the same as the following result. It is the same as the following result. Thank you.